Hello, welcome back. We are going to do some example problems for stereochemistry. Talked a lot about R, S, Fisher, Newman, perspective diagrams and so on, and that's what you're seeing here. We're just going to practice a little bit with, some actual examples. All right. Problem number 1. Draw the diastereomers and enantiomers. Okay, there's only one enantiomer for a molecule of this molecule, 2R, 3S, 2-bromo-3-methoxybutanoic acid. So whenever you have the chiral centers within a molecule, you put the chirality with the number and configuration in front of the molecule. Again, letter separated from number by comma. Same rules. Then you write the name just as you would for an achiral compound. Okay, so let's go do this problem. So there are so that means there are 4 carbons. So we can just do a butanoic acid would be just a butane with an oic acid, which is just carboxylic acid. 2 has got a bromo, and we don't know where. 3 has got a methoxy, and so that's 1, 2, 3, 4. And our job is to find out where these are. So 2 is an R. If it is an R, then it has to go clockwise. If it is an S, it has to go counterclockwise. So when group number 4 is away from you. So if over here, so there should be a bromo here. I don't know whether it's on a wedge or a dash. My job is to find out. So the way this is drawn, let's say if the hydrogen is inside, this is going to be, well, we don't know whether it's R or S. So let's just try 1. If it's not that, then it will be the opposite one. So this is bromine is the heaviest. Then this carbon has 3 oxygen bonds, whereas this carbon on this chiral center is connected to 1 carbon and an oxygen here. So we'll have to put the oxygen in. We don't know again whether it's on a dash or a wedge. So 3 carbon oxygen bonds is definitely higher priority than 1 carbon oxygen bond. So over here, this carbon has got oxygen, 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 3 carbon oxygen bonds and a hydrogen. This carbon here has got oxygen, carbon, and hydrogen. So here, this is definitely going to be higher priority. So this is going to be counterclockwise, which would make it an S. But it says it's an R. Therefore, this is not a wedge, but it is going to be a dash. Now, over here on the methoxy, we want an S. So if it's an S, you want 1, 2, 3. If you put a wedge, it's going to go clockwise. Therefore, we have to put that also on a dash. So that's an S. So if you do this again, let's try it out and see if that's correct. Hydrogen on a wedge. Number 1 is for your methoxy, oxygen, because oxygens are heavier than carbon. So there are 4 things: oxygen, carbon, carbon, hydrogen. Hydrogen obviously is going to be 4. On these 2, where carbon connected to a bromine is going to be a lot higher priority than just a CH3. So that's going to be clockwise, and you might jump to the conclusion that's an R, but wait a minute, that hydrogen is pointing up. So the rule is hydrogen should be pointing away. So therefore, clockwise with group number 4 pointing up is an S. So this is an S, and this is an R. 1, 2, 3, counterclockwise with hydrogen R. Out is R. So now the question asks us to draw diastereomers and enantiomers. So now that we know this, we know the enantiomer is going to be a mirror image of this, which means you'll draw the exact same molecule with the OCH3 and the bromine on wedges. Well, what are the other possibilities? There are 2 stereocenters, so 2 to the 2 is 4. So this and the enantiomer would be 2 of them. The diastereomer would be 1 dash, 1 a wedge, or 1 wedge, this wedge and this dash. So dash, wedge, or wedge, dash. Now, since we did a little bit of practice with Newman projections, and it's always very much easier to see enantiomers and diastereomers on Newman projections. Let's draw some Newman projections for this. So to draw a Newman projection against you have to take this, draw it as a Newman, and then you can draw it as a Fisher. And Fisher would be probably the easiest one to tell. Here's your dot, here's your circle. So on the dot, your hydrogen is coming out. So when you're looking at it, hydrogen is going to come to your left. Whatever is a dash would be on your right, whatever is a wedge would be on your left. So over here, carboxylic acid, bromine to the right, and at the back, methyl comes down, which is the blue, and then OCH3 is going to come to your right, and hydrogen to your left. So that's your Newman. If you want to draw a Fisher for this, take this and make it eclipsed. So rotate the back carbon 180 degrees. And so that is going to give you a molecule where you have carboxylic acid and the methyl being eclipsed. The front carbon was not rotated. The back carbon will have everything 180. This goes opposite, and this hydrogen will also be opposite. Let's draw that out. So over here, we can put this kind of like OCH3 is to your left. And don't forget, top carbon is the most oxidized, and the bottom is the CH3. Now that you've drawn this, then it's a lot easier to go from here, because now we know that those are the two possibilities are just flipping these. If you put a mirror right here, you would get a mirror image for this CH3. Whatever's on closer to the mirror is going to be reflected closer to the mirror. Like if I put my hand closer, it'll be closer even in the image. So that's an enantiomer, and you know you can only have one reflection, right? So then that's an enantiomer. Then the other two possibilities are to have where bromine is right, left, here it's left, right, or they can be right, right, or left, left. Because you have two, you can only have 4 maximum. So we can draw the diastereomers for this with a different configuration here. So COOH, and if you draw the CH3 here, you can draw the CH3 and the COOH on the straight line. You don't want to change that because the rule says carbon chain should be on the vertical line. So instead of having them opposite, you can put them on the same side, bromine and OCH3 on the same side, which means one is the same and the other one is flipped. And then we can also draw a mirror image for this, or another diastereomer where both are on the same side. So you can have this as your other diastereomer. So here is going to be the bromine and the OCH3 on the same side. There you go. So therefore, you can say that, well, we got all of them in 2 to the 2, which is going to be 4. And it says draw the diastereomer enantiomer of this molecule. So you can put A, B, C, D, and then you can say AC and DAD are diastereomers for both of these. The A and B are enantiomers. So let's keep going now. Next question's asking you to label them R or S. What were the rules? Again, find the chiral center, all right? There's only one, which is right here. And then label them from highest atomic weight connected to that center to lowest. So chlorine, obviously, then oxygen, then carbon, then hydrogen. Then it says, put away your group that's the lowest priority away from you, which means draw this on a dash. So how are we going to do something like that? So let's say if I take this molecule here, and let's say this is going to be your hydrogen up here on the top, hydrogen on top, OET, chlorine, and methyl. So we want to put hydrogen away from you. So you have to draw it like this, basically. This has to be going away. All right. So that's one of the ways to do it, is just draw, tilt it a bit and put it in. So if you can do that, so basically you can rotating this a little bit and putting it so that it's up. So when you rotate this like this a little bit, you're going to get OET and methyl going to be coming at you, and then chlorine and hydrogen will be away. Then you can do 1, 2, 3 like this, counterclockwise, hydrogen away from you. That's an S. Now, there's another way that you can do if you're too lazy to like twist your brain around this. The rule is if you do 2 switches, it's going to be the same molecule. If you have one chiral center like this, and if you do 1 switch, it's an enantiomer. So let's try that out. Let's do 2 switches. So I want to put the hydrogen where the chlorine is. So let's switch that. Do 1 switch like that, and do the other switch between the methyl and the OET. And so now if I do that, 2 switches, it's the same molecule. So here you're going to have hydrogen go where the chlorine is, and chlorine go where the hydrogen is. In the front, we're going to switch OET and the methyl. So methyl comes over here, and OET goes over here. Okay, now hydrogen is inside. Let's try this out. 1, 2, 3, counterclockwise. S, so that did work. Well, let's see if 1 switch gives us an enantiomer. Maybe, maybe not. Let's try it out and see if that's true. Because I want the hydrogen to be away, so I'm just going to switch the hydrogen and the chlorine. So hydrogen goes where the chlorine goes where the hydrogen is. Keep these the same. And that's a methyl. So again, 1, 2, 3, clockwise R. So you know that worked. So that's one way to do it if you had just one chiral center like that. Let's look at this molecule. Is this R or S? Well, first of all, find the chiral center. Oxygen's not a chiral center. These are CH2s. CH2s are not chiral centers. And alkenes are sp2, so are not chiral because they're flat. Same with sp. They have many planes of symmetry, so these are not chiral either. So that's our only chiral center here. Okay, which means you have this carbon coming out and you have a hydrogen, and it's already drawn inside for you, which is great. So then we have to go in on this chiral center and see what are the atoms connected directly to that chiral carbon. Over here is an oxygen, so that will be higher than carbon, so that will be number 1. If you go over here, this carbon is connected to a carbon, carbon, and a hydrogen. If you go to the right, this carbon is connected to carbon, carbon, and a carbon. Well, carbon, these are the same, but here, this carbon has higher priority. It's a heavy weight. So you gotta give respect to this group next. And then you can do your alkene. So 1, 2, 3, hydrogen's already away from you, don't have to worry about that. 1, 2, 3 clockwise, this is going to be R. Look at this molecule. Fun, fun, fun. What are you going to do? Get under the chair and look at it? That's one way to do it. And make an S. Or you can redraw this. Let's redraw this molecule. The way to redraw this is to look at it like this from the top. So let's look at it from above and just draw it out just the way you're going to see it. Let's say you're going to look at it like this. So which means you're just going to see a 6-membered ring flat. Over here you're going to see a carbonyl, and here you're going to see a methyl up and an NO2 down. Now you can flip this and draw it out so this whole thing is 180 degrees on the other side. That's fine too. All right, so now let's see where the chiral center is. These are CH2s. They are all achiral. This is a carbonyl sp2, sp. They're all achiral. Here is a CH3. There's already 3 hydrogens there. That's achiral. So it's probably, and even NO2 is going to be sp2. So that's achiral. There's only 1. So then we have to go in and label it and see which one is the heaviest. Obviously, nitrogen is going to be heavier than the carbon. So this carbon is connected to 1 carbon and 2 hydrogens. So this center is connected to 3 carbons, 1, 2, and 3. And then you have to see which one's heavier. This is hydrogen, hydrogen, hydrogen on this carbon. That's nothing. So this carbon has got oxygen, oxygen, and carbon. Well, that's way heavier than this one. So that's 1. This is 2, and this is 3. 1, 2, 3 going clockwise. Now don't jump off your chair and label this R. Number 4 is coming out. So clockwise with 4 coming out is S. All right, let's do this one. I rewrote that for you. So here, what would you want to do? Well, 2 things. You can draw it as a fissure, and then the fissure is a little easier to do as an R and an S. For example, here's the fissure here, and you can see that if you want to do R and S, we can practice on this before we do that. 1, 2, 3, counterclockwise, hydrogen out is R, and 1, 2, 3, clockwise, hydrogen out is S. See, the R and S are perfectly reflected over here. So that's one way to do it, and that's probably what I would suggest, except right now I don't have space to draw the eclipsed and so on. So I'm going to do another way of doing this, which is pretty much looking at it on the side. If you look at it on the side here, you will see CHO and last carbon here, OH, coming down. So CHO is going up. This is your dot, and that's your circle. Your dot and circle are kind of like your central carbons there. CHO is going up, and OH at the bottom, at the back, is coming down, this carbon. Then towards you, that means coming out on a wedge, is a fluorine that's attached to the carbon that's attached to the CHO. And towards you, coming out as the methyl, CH3, that's going to be on the circle carbon, on a wedge. You got that much, right? That's all you really need to do R and S here. This fluorine has got on the opposite side, so away from you, which means it's going to be on a dash, is a CH3. And if you go to this away from you on the opposite side, so these are going to be, when you're looking at it, these are your wedges, these are your dashes. This is up and down, pretty much what we've drawn here. That's your hydrogen. Now we can do R and S just by labeling it. So if I label this, so we have a chiral center here and a chiral center here. So the dot and the circle both have 4 different things on them, so which means they're stereocenters. Fluorine obviously is heavier than carbon. So this chiral center has got carbon, 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 fluorine on it. So number 1. And between these 3 carbons, this carbon is connected to 1 oxygen, 1 hydrogen, and 1 carbon. If you take this carbon here, that's connected to CHO is actually C double bond HO. So it might help to sometimes draw out a Lewis structure for this instead of a condensed structure. So over here, this has got CO, CO, and H. So OOH, because these are all carbons. We're just comparing what else is attached to them. So these methyls are nothing. So between these 2, you can see this is going to be higher priority. So 1, 2, 3, clockwise with group number 4 away from you. You don't even have to rotate this in your head. So this is going to be R. And over here, we can do the same thing. 1, again, this carbon is heavier than that, and 4 is going to be hydrogen. 1, 2, 3, clockwise is going to be R. So we have an R stereochemistry for this molecule. Now if you don't want to look at it on the side, you can also do a eclipsed and do a fissure and know that that'll be fine. So over here, here's a big molecule. Where do you even start? Just start from one end and label them. Over here, you can see that this carbon is going to have 1, 2, 3, 4 different things, which means you are not going to have a plane of symmetry. sp2, sp2, ch3, ch2, oxygen, ch3, these are all achiral. Triple bond, achiral. So there's only this guy, and this has 4 different things. So this is going to be again chiral. So let's work on this, label them 1, 2, 3 according to molecular weight. This carbon, chlorine, is heavier than these 2 carbons. So we have a carbon here that's connected to carbon, carbon, carbon. Now there's a carbon here. This carbon is connected to an oxygen. So over here, just right on there, you can say that this is going to be number 2 and this is number 3. So then you go counterclockwise, and before you jump off your chair and label that an S, look for number 4. Number 4 is coming at you, so therefore it's an R. Over here, do the same thing. This carbon has got carbon, carbon, carbon bonds. This carbon has got nitrogen, 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 3 nitrogen bonds. This carbon has got carbon, carbon, and carbon. So then we have a competition here. So we know this is number 1 because nitrogen's heavier. Because all 3 of these are carbons, that's why we're then going into the side chains that they are connected to. So carbon, carbon, carbon here. So because we have a tie here, we have to keep going and see which one has got people in higher places, heavyweights. This one's connected to CH3s, so HHH. Whereas this one's connected to a carbon that's connected to other carbons. So therefore, this is going to be, again, just like here, heavier than this. So 1, and then 2 here, and 3 here. So 1, 2, 3, going counterclockwise, right? But hydrogen is in. So therefore, this is an S, and this is an R. So those are things that you'll just get mainly from practice. This is for this one. This is the exact same thing as this molecule. I just don't want you to think this is something to do with this. These are together, these are together, and these are together. This is the same as this. All right, so let's look at these guys. Okay, I know this is kind of heavy for you, so just pause, go over to your kitchen or wherever, grab a drink, put your feet up and just watch. After some time, you will see they're very, very similar, and then you kind of get the hang of it. Let's look at this. So here, 3 molecules. They're asking what's the relationship between A and B, B and C, A and C. First thing to notice is that they're all fisher. Do they have all the carbon chains on the vertical line? Yes. You don't need to change anything. And they also have the same groups on the top, same groups on the bottom. So this is a good place to start. So by definition, molecules that are reflected and they are non-superimposable are enantiomers. So you can see this and this. These are reflected. So A, B are both enantiomers. Let's look at B and C. If I draw a line between B and C, are they mirror images? What do you think? If this is a mirror image, that's correct because it's further from the mirror, this is further from the mirror. But look at this. This is close to the mirror, this is further from the mirror. So these are not mirror images. But they are stereoisomers because every single atom is connected to the exact same things. Stereoisomers that are not mirror images, by definition, are called, that's right, the D word, diastereomers. All right, let's look at A and C. Same deal here, A and C. One's the same, the other one is switched. So those are also diastereomers. Good, let's move on over here. Here's a molecule and CH2OH, and they're the same things. And it's got these reflected. What do you think? Mirror image? Looks like it. But wait a minute. You know that the 4th rule for the Fisher projection says, so you can take a molecule like this, and if you rotate it like this, it's the same molecule. But if you flip it like this, then it's not the same molecule. So you cannot take this molecule and do a 90, because that really means something else for the vertical and horizontal. But you can take a molecule and do a whole 180. Let's do that over here, because the top and the bottom are the same. So maybe you can do that. So CH2OH, 180-degree rotation. This comes down, this goes up. So if I label this 1, 2, 3, 4, now 4 is on top, 1 is at the bottom. All these groups are also going to be 180 degree rotated. H, H. Look at this. E, and I will put E prime, which is the same thing as E actually, so I should just label this E. D and E are exactly the same. I can take this and put it right on top. They're superimposable. So if they're superimposable molecules, it just means they're the exact same molecules. They're identical in every way. All right? So don't let this fool you guys. It does look like a mirror image, but if you can rotate it 180 and it's the exact same molecule, then they're going to be identical. Another thing to notice here is if you take this molecule, you can cut it in two like this. You have over here, right in the center of this molecule, a mirror plane of symmetry. Same here. Same here. When you have an internal mirror plane, that molecule is called a meso compound. Internal mirror plane. Meso. So these two are like meso compounds. Meso compounds. So the molecule and its mirror image would be meso compounds. That would be D and E. Actually, in this case, it's identical. Let's keep moving on. So here's a molecule, G, and here's a molecule here. It looks like the CH2OH is not reflected. And CH3 is, but everything seems a bit switched here. Look at this, the CH2OH is actually over here. So this is going to be, well, let's look at it, okay. So here's your, let's say we have a molecule like this, CH3 hydrogen, bromine, and CH3, CH2OH, Br. If you look at this, you can see CH3, CH2OH, bromine. The rule says push the CH2OH at the bottom. Actually, it should be way on the top, but before that, let's put it at the bottom, so at least it'll be on the vertical line here, because we have to put the most oxidized carbon on the top. So someone really just drew this without knowing the rules, but we got to correct it. So to do that, we have to do a rotation. So then the bromine's going to come on this side, and the methyl's going to come on this side. So basically, think of this as a 3D. This is going to be coming out, and this is going in. So you're going to do just a 120 degree rotation. This goes here, this goes here, and this goes here. 120 rotation. Now we can redraw this like this, the CH2OH. Methyl is here and bromine is here. Then you can draw the top here. This is the same as this. We didn't change this, bromine, hydrogen, methyl. Now the rule says CH2OH should be on the top. So we can do a 180 degrees on the plane rotation. We'll do a 180 degree rotation for this. So the up goes down and the down goes up. So this goes up, CH2OH. CH3 comes to the side. Everything's on this side is going to end up on this side. So CH2OH now, when you rotate this, the bromine is going to come on the left. This bromine is also going to come on the left. CH2OH, CH3Br. It's connected to a CH3 and a Br. So what's here will go here. What's here will go here. So they will like completely switch places. So methyl here would have the bromine on this side and hydrogen on this side. Now this is the same as this. We just did two operations to it. Now you can compare G and H right here. Here we have bromines on the opposite side. Here they're on the same side. All the other atoms are connected to the exact same things and they have the exact same formula, and therefore these are stereoisomers and not mirror images. So G, H are, do I hear a drum roll? What is it? Diastereomers. That's correct. Diastereomers. So you got to sometimes work at it because it's not really obvious. Ready for another one? Take a break, come back. Let's look at this and let's look at this. What is the relationship between these two? Well, if you look at it like this and stare at it and stare at it, it may not be too obvious. So let's draw a fissure so we don't really mess it up. Or we can draw a fissure is about the same as drawing an eclipsed Newman. So let's start there and see if we can figure it out from there. Since we have carboxylic acids on both sides, that might be something that's easy to do. So therefore, let's try to get both the carboxylic acids on the same side. So the one on top is already there. Let's rotate the bottom 180 degrees. So that is going to be the same as drawing it out like this. I'll just draw it in a different color. Carboxylic acid, OH, H. And at the back, carboxylic acid now goes up, which means everything goes 180 degrees. This goes 180, this goes 180, and this goes 180. So both the hydrogens are going to be on the same side, and the hydroxyls are going to be on the same side. Let's do the same thing over here. So we are going to keep the back the same because we want to compare an eclipsed, and the back is already up. So why mess it up? Keep it like that. And take the front carbon and rotate it 180 degrees. So carboxylic acid goes up, then everything else is going to do 180. OH is going to come here, and H is going to come here. So you might look at this and say, these look like very nice mirror images. But remember, there's one more thing you got to find out. You got to find out if they are meso. So if you look at it like this, you can see you can cut it in the middle like that through that circle. But if you're not sure of that, let's draw a Newman, which is why Newmans are so useful. I guess that's why they gave that guy a Nobel Prize. You can pretty much see it on a Newman. So on a Newman, both hydroxyls are on the same side. Carboxylic acid, OH, H. And over here, carboxylic acid, OH, H. So you can see there's a nice mirror plane of symmetry right in the middle of this molecule, and you can cut it in two beautiful halves and they will overlap. So this is called a meso. What about this? Exact same deal, guys, right? So you can see that over here, the carboxylic acid, hydroxyl, and hydrogen are kind of flip, but so is the bottom, and that would be okay if it's not a meso, and you would have mirror images. But since this is a meso, you can see how you can take this, do a 180-degree rotation, put it right on top of this. So I and J are meso, and they are identical. It may not be obvious here, which is why we got to do all these other operations. Moving along. Let's look at these guys. What's the relationship between these two? Well, this guy looks like a horse, and this guy looks like something with spikes on it. But we got to look at it at the same configuration, at least drawing-wise. So compare a Newman to a Newman, compare a fissure to a fissure, compare a flat to a flat. And so let's do that. So let's draw this flat, or a perspective to a perspective. So over here, if you draw this out as a chair, when you're looking at it from above, you're going to see a flat chair. This is going down. So let's say this is 1. At 1, methyl is going down. At 2, ethyl is going up. So let's say this is K and this is L, M. So here, if you take this and put a mirror below this chair, you will see the methyl that's pointing up will be pointing down. Ethyl that's pointing down will be pointing up. And so therefore these two are going to be enantiomers. Let's take K and M. First of all, again, you got to draw this out in the same perspective. 1, 2, 3, 4, 5, 6. Let's see. So that is going to be 1 and 6. 1, methyl's going down. If you put the hydrogen, it'll be a lot more obvious. And here too, you can put the hydrogens going up, and so ethyl's going down. So over here, up, down, down, down. So therefore, they are going to be diastereomers. And even these, L and M, would also be diastereomers. Well, here's another one. We're going to compare a Newman to a fissure. It's not a good idea, well, unless you're like an expert and you can do this in your head and see, okay, we're going to then align CHO and OH, OH is going to come to the same side, and you can do it in your head. But if you're not there yet, don't just waste an attempt. So just do the same thing we've done before. Take this and align this, make the eclipsed Newman. Look at it from below and draw it on the grid. So over here, we can go 180, which means all the groups are going to rotate 180. We can keep the one in the front just like it is and just rotate the back. CO2H is the same as COOH. It's the same as drawing it out. So here you have your CHO going up, and then you're going to have your hydroxyl come to the same side, and the hydrogen come to the same side as this hydrogen. Everything goes 180. Now you can look at it belly up. Look at it like this. CO2OH and CHO are going away from you, which is what it's on a Newman. So this and this are going to be going away from you, and CHO. I'm just writing it out. OHs are going to be to your right. Hydrogens are going to be to your left. Well, what do you think about both of them? It's pretty obvious, isn't it? These are reflections of each other. They're both close to the mirror, the hydroxyls. And I did draw these out. That doesn't mean they're not mirror images. They're the same thing, COH and COOH. There you go. So N and O are enantiomers. All right. Here's a perspective and a numen. Again, try to draw it in the same format so it's easy for you to see the sides. Otherwise, sometimes you might assume certain things that are not correct. So here is your CH2OH. So that's your CH2OH. That's on top. Your ethyl is at the bottom. So therefore, you should probably be looking at it from this side because we want to put that on the top. So we can draw a numen for this CH2OH up, and here we haven't drawn the hydrogens. Hydrogens would be here. Another way to do it would be, instead of drawing out the whole thing, is to make sure that you have an R and S match, or whether it's flipped or not. If R is reflected, it will be an S. If it's the same, then it will be an R. So over here, when you look through here, OCH3 is on your left, hydrogen is on your right. So whatever is on a dash line would be on the right-hand side. Whatever is on a wedge would be on the left-hand side when you're drawing a numen. And here's your ethyl. It's going to have like a tail. Now you can rotate this and you can draw the numen. So if you rotate this 180 degrees, your ethyl is going to be on the same side as CH2OH. And the OCH3 will be on the opposite side of the OH. It will be over here. So I'm just going to draw it like this. CH2OH again, H, and OH on the front carbon is just like you see it, right, left. But the back carbon is switched. So OCH3 is now going to be on your right. And H is going to be on your left. Now you can compare these two. This is the same. This is flipped. Therefore, P and Q are diastereomers. If they are enantiomers, both will be flipped. If they are the same, both will be the same. Another way to do this is to do R and S and see if this is the same. So for this carbon, we can number this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This might be easier for some of you instead of writing it all out. This is the same as this, and this is the same as this. Over here, 1, well, this has 2 hydrogen. This is a hydrogen and a carbon. So this is clockwise, hydrogens away from you. Therefore, that should be an R. Over here, oxygen obviously is heavier than a carbon. So this is number 1. And this is number 2 because this carbon is a lot busier than this. So 2 and 3 clockwise, hydrogen away from you, and that would also be an R. RR. Then you come over here and do the same thing. So here's 1, 2, 3 counterclockwise with hydrogen on a wedge. Therefore, this is going to be an R. Over here, 1, 2, 3 clockwise with hydrogen on a wedge coming out at you. Therefore, it's going to be an S. R, S, R, R. Therefore, they're diastereomers. That would save a lot of time if you want to just label it and do it. But sometimes you may have a problem trying to do R and S on a numen, which means a lot easier if you draw it as a fissure. And you can see on this fissure, you could do 1 and then 2, 3 counterclockwise, hydrogen out is R, and 1, 2, 3 clockwise, hydrogen out is S. And so if it's an enantiomer, you would expect the opposite here. 1, 2, 3 clockwise, hydrogen out is an S, and 1, 2, 3 counterclockwise, hydrogen out is an R. So you can see enantiomers RS reflected as SR. Diastereomers would be different. RR would be RS or SR. Very good. One more, guys. It says this one, circle the chiral centers. Maybe I should have had it way up there. Let's see. So pH is a benzene. Benzene is all sp2. So that's all achiral. Here's another carbon, sp2, oxygen, sp2. Our hydrogen can invert, you know, like the Walden inversion. I don't know if you remember that umbrella we were showing you, but you had to go all the way to like a minus 78 to freeze one of them. Therefore, you just take a snapshot. It's going to be somewhere in the middle. So we typically don't consider this unless it's at very low temperatures. You can't really isolate them. This carbon over here, 1, 2, 3, and there's a hydrogen. So that's a chiral center. This carbon, this is some probe molecule. 1, 2, 3, and a hydrogen. So that's also going to be having 4 different things, no stereocenter. Anytime you see an SCH2, CH2 is achiral because you can have a plane of symmetry that cuts through those hydrogens and you can get 2 equal halves. If you take this, again, 4 different things, no plane of symmetry. If you take this one, this is different from here, this is different from here. All of these are different. So therefore, that's a chiral center. This is a CH2, achiral. If you take this, again, 1, 2, 3, 4, all different, that's chiral. So 1, 2, 3, 4, 5, you will get 2 to the 5 stereoisomers because N is going to be 5 or number of stereocenters. So that's what, 32? That many possibilities, but nature will only make one of them. Okay, it's got the enzymes to do only one. So in summary, I'd just like to say, practice, practice, practice. Practice makes perfect. Bye.